Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Yun Zhang with us today. Hi, Yun.
Hi, everyone. Hi, Frank.
Well, thank you so much for agreeing to talk about your very lovely article.
Yeah, that's my pleasure.
Cool. And Yun, where are you located at?
I am located at College Park, Maryland.
Maryland. Very nice. It is April 27th of 2023 as we record this. And Yun, is spring in the air on the East Coast? Summer?
Yeah, the weather is lovely outside.
Oh, lovely. Oh, okay, this is good.
Yeah, we just have like a cherry blossom like 1 month ago. And now all the trees are growing.
Very good. I was in DC about I guess about a month ago, and we were like a week early before the cherry blossoms. So none of the trees were still all bare. So it's good to hear they finally came out and checked it out. So very cool. Good.
Yeah.
And Yun, what do you like to do for research?
So yeah, my research is in the field of planetary science. And I would like to understand how the small body evolve and evolution, and use them to understand how the solar system is formed and how the chemical composition can be deposited in different bodies. Indeed.
Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It's open access, people. You can go get a copy for free. It's the open access era. And GTASB 3D, a novel 3D framework for modeling thermal evolution and rarefied flows in porous active small bodies with various shapes. And Yun, take us away.
Okay, yes, thank you. So the idea to carry out this study is to understand how the volatiles evolve in these small bodies. So now we know, like, we have comments, which is volatile rich. And now we also have the main belt comment, which is also may have some water ice in their bodies. And how these ice can be preserved, that will be related to their thermal history. And we need a model to properly simulate their thermophysical process and to assess how these water ice and other volatiles evolve in such a body. So that's the motivation to build this model.
Cool. Cool. Okay.
And so when we start this study, we would like to actually simply start from like a 1D model to simulate that. And then we find out there are some boundary issues when we use the 1D models, especially when we consider the sublimation and the flows of the gas in such a porous body. So then we need to actually use maybe a 2D or 3D model to better characterize the thermophysical process as well as the gas flow, and to also account for the lateral heat conduction in such a body. And before this study, we already have multiple 3D models that can be applied to study the thermal evolution of spherical bodies. Because for the spherical bodies, it's easier to like use the spherical polar coordinates to do the domaticization and to do the mathematical calculations. So that's easier for spherical bodies. But now we know that for most of the small bodies that are smaller than like 100 kilometers, they have irregular shape. In that case, since the irregular shape may bring some a larger surface to mass ratio, in that case, the thermal process may not be equivalent to a spherical body. So we really want to like have the ability to simulate the thermal process for irregular shaped body and also in 3D. And that's a difficult things to do, but we kind of read through the literature and found there are one of the so-called meshless method, which is called the generalized finite difference modeling method. And this method could help us to discretize irregular shape domain and then to solve the partition differential equations and to simulate the thermal process for small bodies.
Okay.
So that's our idea begins.
Okay, very good. So this is a meshless scheme. All right, very good. Going to be.
So in the introduction, there are some detailed reviews about the current development of these fantastic thermal physical model already existing. And so our contribution will be to provide a way that can simulate irregular shaped bodies in 3D.
Cool.
And we also, this model also handle the heat conduction and the ice sublimation simultaneously to allow for model a commentary like body.
Okay. All right.
And so in the section 2, we will have a detailed introduction about our thermophysical models. So this thermophysical model has been utilized in most of these common numerical studies.
Okay.
And so we can quickly go through that.
Sure.
And yeah. And the table 1 and 2 will have summarized the parameters has been used in these models. As you can see, these there are many parameters, and some of them are still largely unknown, but it is sort of constrained by the past mission, like the Rosetta mission.
Okay. Okay. Ooh, now there's a word I haven't heard. What is tortuosity?
Oh, tortuosity, just it describes how the gas flows through a porous medium. So for the porous medium, because the tunnel and the channel is not straight, so they can have twisted. So the tortuosity will describe how this channel turn around and to describe how difficult gas can flow through this porous medium.
Thank you. I learned something new. Awesome. Very good. Thanks.
Yeah, thank you for the questions.
Sure. And the governing equations, we will have an energy conservation, of course.
Yes, and we have energy conservation, and we also have the if you go to above in the equation 2, we have the gas mass conservation equation, and we also have the ice mass conservation. So by solving these 3 conservation equations, we can obtain the conduction of heat and also the consumption of ice and the density, the float of the gas in the porous body.
With you. Cool.
Yeah. And then for the equation 4 is used to describe how the float of the gas in a porous body is driven by their density and temperature difference.
Yes. Yes.
And the equation 5 is used to describe how an ice can be supplemented according to the surrounding pressure and will be supplemented to provide more gas into the pores in the body.
Okay, so this is a reaction rate, right?
Yeah, yes.
Got it. Okay.
And if we, then this is the governing equations we want to solve, and because this will govern the process happen in the interior of the body. And to properly solve this equation, we also need some boundary conditions. So in the following, we also include the boundary conditions which consider the solar radiation and the thermal conduction, as well as the latent heat caused by the ice sublimation to form the boundary conditions on the surface.
So this is a moving boundary.
This is not a moving boundary. The this is kind of like a two mixture. So the body we are simulated, they contain refractory dust and also some volatile ice. And the ice, they can retreat. The ice film can retreat. Correct. But the boundary of the dust, we are assumed is fixed. But
Got
in reality, there will also be some erosion for the dust layer. But
Right.
currently in our model, we haven't accounted for that.
Okay, I'm with you.
That's a very good question.
Thank you.
And we also formulate the equation A to solve the gas boundary conditions. So this is also in order to provide the gas boundary conditions, we consider there is a infinitely thin surface layer, and we will form the conservation equation on the thin surface layer.
Yeah.
So by accounting the ice sublimation and also the gas that is flow from the subsurface to the surface.
Okay.
So the outgassing of the comment will be equal to these two combined, as shown in the right side of this equation A.
Right. Okay, cool. I'm with you. There's your normal vector. Yep. Very good. Cool.
So, and of course, in this equation is just like an approximation for the physics we consider in the surface of a cometary body.
Sure.
And if someone want to treat this more accurately, then they would need to evolve a simulation of the coma, use like some kind of discrete, the direct simulation of Monte Carlo method.
Right.
And yeah, that's something we would like to proceed in the future to check with this.
Okay, we'll come back to that. Okay, very good. I don't think we looked at table 2. Let me take a peek at table 2. Okay. Boop, 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 boop. Okay. Good. Very good. Very well documented. Very nice.
Yeah, the difference between table 1 and table 2 is like the table 2 is the parameters are provided by equation. Then the table 1 is just value.
I'm with you. Yep. Yep. That's mainly going to be the physics modules, basically. Okay.
Yeah.
Cool. Very good. Moving lots. Okay. Very good. And then we got our boundary conditions, and then we come to the model parameters and the GFDM.
Yes. So now we have like the equations we want to solve, and now we need the techniques to solve this equation. So previously, as I talked before, they often use like the finite difference or finite volume method to solve this equation. So that can be only limited to some irregular boundary, like irregular domains for spherical or for the rectangular domains. But now with the generalized finite difference method, which is measureless, in that case, we can randomly distribute the nodes, and we can use that to solve this partial differential equation.
Good, I'm with you.
Yeah. So then this idea of this method is based on the least square method, and they will use the Taylor series expansions to expand the nodes in terms of its neighbors, and then they will use the moving least square approximations to derive the formula for the partial differential equation. So in the section 2.2.1, there is a formula to describe how we use this the Taylor expansion and also the moving least square to derive this the partial differentiation.
Okay. All right. I'm with you.
Yeah.
I understand. Okay, and there's our Taylor series expansions, U and B. We want to minimize those. Okay.
Yeah. So the maybe the most importantly, although the equation here seems a little bit complicated, but eventually when we arrive at equation, can we go below a little bit?
Yeah, sure. 20, 21.
Yeah. Then eventually when we arrive at equation 21, then we can form a very simple formulate, and which describe the partial differential, which is the du and as given in equation 15.
15, yes,
Yeah.
there we go.
So then we can form these partial differential equations equal to a coefficient matrix and multiplied by the value of the neighbor node for the sorting
Yes.
the sorting node.
Yes.
So
okay.
yeah, maybe I did not explain that well. So for the x0 and is the node we want to solve for the equation.
Yes.
And the u0 is the parameters or the state of this node, like the temperature of this node.
Okay.
And now in order to solve the temperature of this node, and we use the temperature of the other nodes, the other neighbor nodes from the nodes 1 to node ms, and then we use this the coefficient matrix lambda. We found this coefficient matrix lambda use the GFDM method.
Yep.
And now all the differentiation, the partial differential du will be equal to this lambda multiplied by all the state variables in the neighbor list.
Okay.
So this the final format is very simple. So, and if we don't consider there is like the erosion of the dust, so then this body, the shape of this body will remain the same in the whole simulation.
Yes.
In that case, we only need to calculate the coefficient matrix lambda once in the beginning of the simulation, and we can use that for the following. So that's really help to ease the computational burden and make the code efficient.
Definitely. Okay, I'm with you. Very good. Okay.
Yeah.
And time integration.
So yeah. So now since now we have used the GFMD to solve the space partial derivatives. And now we also need to use that to solve the evolution of the temperature in terms of the time. But and the most of the method have like used some explicitly Euler method and also like the semi-implicit Kronecker-Nicholson method.
Yes.
And also some of them use some implicit method.
Yep.
And yeah, in general, it will be much more efficient if we can use like implicit method, because in that case we can use larger time step.
Right.
Yeah, but that's much more easier to be implemented in a 1D scheme. But since we for the 3D scheme and also for the equation, the 3 governor equation we want to solve here, and it will be not very efficient to use an implicit scheme, because also the parameter, as I show in table 2, these parameters are all temperature dependent. And when using an implicit scheme, they need to use some kind of iteration method to let the solution to converge into within a given threshold. But in a 3D framework, it will be very hard to use an implicit scheme to make the convergence, because all these parameters are sensitive to the temperatures, and how to solve the inversion of the matrix in the implicit scheme is also troublesome in this case. So that's why we still use a simple implicit Euler method in this code to solve this time evolution.
I'm with you.
Yeah, and these methods is also provide an ability to make the code easy to be parallelized. So we can take the advantage of the current high performance computing to make the code parallelized and to compensate for using a very small time step. So in that case, we can still achieve efficient simulations.
So is this MPI parallelized or OpenMP or both?
This is OpenMP.
OpenMP. Okay.
Yeah.
Yep. Okay, and then we got algorithm for the solve. Okay.
Yeah. So I think before maybe the method seems a little bit confusing, but in order to provide a more clear picture to how to conduct this coding, we summarize in this 2.2.3 how to the basic step of using this method.
Tailor, integrate. Yep.
Yeah, so then following this step, it's actually quite easy to implement this code.
Cool.
And we have implemented this code in a C++ code.
Okay.
And yeah, we are hoping to make this open source in the near future.
Yes. Good. Yay for
Yeah.
open source. Okay, very good. Yeah, it looks like we got a mesh here.
Yeah, so yeah, here is give one of the example like how we discretize one bodies. So in one thing I did not mention is actually we are actually looking at that is like things in the GFDM model, although we can like distribute the node randomly in a domain to solving the equation, but we cannot make the like the spacing between different axes, like between different direction, to be to be different too much. So like if we use the spacing is 10 times larger than the axis spacing. That will cause some singularity issue for solving the inverse of the matrix, as I introduced before. So yeah, so in that case,
conditioned, I should say. Right.
Yeah. So in that case, we can use this node randomly, but we still need to ensure they are not divided or biased towards some certain direction.
Yes.
But when we solve the thermal equations, we know that on the surface, on the boundaries, the temperature gradient will be the highest.
Yes.
And in that case, we need to use a very fine spacing in order to solve the heat conduction near the surface along the normal direction.
Yes.
But if we and that's usually need to be smaller than the diagonal thermal skin depth, so which is like on the order of 1 centimeter something.
Okay.
Yeah. So in that case, if we use a spacing of a centimeter, then in order to describe a kilometer size body, we will need to use like trillions of nodes that is impractical
Right.
So yeah, so then we come up with this hybrid comp method. So we use 1D surface layers to solve this steep thermal gradient, and then we construct the interior using the 3D method.
Got it.
So in that case, we can avoid the singularity issues, and we can also capture the steep thermal gradient while in the code.
Yes.
Yeah.
I'm with you.
Although these things a little bit like artificial, but we have a carry out test in the appendix C to test the influence of how we set up the 1D surface layer, and we found that the result is not sensitive to that. So, which makes the code reasonable.
Yes, a little comforting there. Very good. Yes. And we'll visit that appendix in a bit. Okay, so there's our 1D surface layer, and we solve on the interior.
Yeah.
Pull in semis. Okay.
And the other issues for this for solving this problem is like since we want to solve the thermal equation as well as the gas and ice activities equation. For the ice and gas, the time scaled for the ice sublimation and gas flow is very small. It's like smaller than 1 millisecond. So in that case, we need to use a time step smaller than that to guarantee the properly the solution is accurate. But
explicit method, yes.
Yeah, but it's like infeasible to use such a the small time step.
You won't get anywhere.
Yeah. So yeah, we will wait forever to obtain one solution.
Just one thermal time scale, for example. Yes.
Yes. And in contrast to the small time step for solving the gas and ice, and the time scale to solving the temperature, as shown in the delta T here, is like on the order of 1,000 seconds. So in that case, if we use this time step, then the equation will be solved very efficiently. Okay. But this time step won't allow us to solve the gas and ice equation properly.
Right.
So that's why that's why we come up with this like a two-step time step idea. Okay. So basically, we assume like the temperature is the temperature equation will be solved by the larger time step, and then we use a small time step to solve the gas and ice mass conservation equation.
Okay, so it's sort of like a sub-step cycling.
Yeah, it's like a sub-step cycling. Yes, that's very accurate description.
Okay, I'm with you.
Yeah, and also since although the time step for the ice and gas activity is extremely small, but they can achieve the equilibrium state very quickly. So, yeah, so in that case, we only need to use several iterations using this small time step to achieve an equilibrium state. And once the equilibrium state is achieved, then we can just extrapolate to the next thermal time step, then to integrate the whole the conservation equation.
Okay.
So
yeah, all right.
So that's really save a lot of time.
A lot of time.
Yeah.
Yes. Cool.
So as the figure 2 has described this scheme. So yeah, so every time we will check if the equilibrium is achieved in the center node. So we set up epsilon g, which is we usually use like 10 to the minus 6 or something to check to set up the equilibrium threshold. Right. So once this is confirmed for all the nodes, then we assumed the gas and ice will achieve the equilibrium, and then we don't need to do any small time step integration.
Okay. Very good. Okay. And then we have our mouse. And so we're going to do a semi-implicit crank on that thing. Here's the step.
Yeah. So here gives more details about how we do the extrapolation.
Yep. And then we have some validation and performance.
Yes. So since this study is presenting a new method for the thermal simulation, so we definitely need to validate that. And so we are using the previous study, which has provide a pretty good validation point. So we use the same setup to make a 1:1 comparisons with their studies.
Yes.
Yeah. So this study is carried out by Dr. Gribel's laboratory. I hope I pronounced that correct.
It's probably better than mine, so okay.
Yeah, and in their study, they also compute the 3D thermophysical evolutions for spherical bodies. Very nice. And they use like 2 different schemes for their computations. So and then we would like to use the same setup, and we simulate the similar evolution of spherical body. Okay. And in the figure 3, here is a result for our computations, and which provide the temperature distribution on the surface of this body. And in the paper of the Dr. Grumberg, they also have these figures, and we make direct ice by ice comparison, and the results are very similar.
Cool.
Yeah, the only major difference is the temperature at the pore region is a little bit different.
Okay.
So as we discussed in the text. So, and the temperature the distribution of the temperature and the maximum temperature are very close for both of these measures.
Okay.
But the minimum temperature we obtain from our coat is slightly cooler than their coat.
Okay.
One of the reasons we think will be like related to how the port temperature is actually solved. Because in our method, we use Cartesian coordinates to solve the equation. Yes. So we don't have the singularity at the pore region. But when someone like formula the partition differential equations in spherical coordinates, in that case, they will have the singularity in the pore region.
Right.
And so in that case, the temperature on the pore region is not accurately solved.
Right.
And they may be approximately of the surrounding region.
Cool.
Yes, so we think that may be the issue why we get a lower temperature in our case.
Okay. Good. Good. Yes, yes, yes. We covered that. Oh, and here's an example of one. Okay.
Yeah, and the other validation we need to do is to make sure the interior temperature profile is correctly produced. And there is a paper by Schultz-Gopher and Hensch. They have used like mathematical models to derive the interior temperature profiles based on the Legendre polynomial decomposition.
Yeah.
So yeah, so we
20.
Yeah, so it's like the higher degrees, it seems to get maybe a better more equilibrium temperature profile. So this figure 4, we compare the temperature profile with theirs. So the color. The color patch is what we obtained from our simulations.
Okay.
And the contour is the theoretical results. So which are matched with each other pretty well.
Yep.
So yeah, in this case, we confirm that the interior temperature and has also been well produced and simulated in the code.
Cool. Cool. Okay, I'm with you. Bang.
Yeah, thank you.
Thank you.
And so, and the other test is to make sure the code is indeed it can solve the conservation. It can guarantee the conservation of these variables, because although we are solving the conservation equation, but due to numerical issue and also the methods how to do the partial differentiation, we may actually encounter some non-conservation results. So in order to validate that, we check the conservation accuracy after equilibrium has been achieved. So as shown in this figure 5, and which shows the evolution of the temperature difference in the interior, as shown in the A panel. And the panel B just shows the thermal energy balance in the surface. So as we can see that when the heat is propagated into the interior, the difference and the temperature increase will increase largely, like in the first 1,000 years. And then after like 6,000 years, the interior temperature and the the surface energy balance will be reduced to 0.
Right.
And after that, it will still maintain in that state. So which provide validation that testing our code is conserved.
Okay, good. It's always nice to have conserved quantities.
Yes, and we also show that the time to achieve the final thermal equilibrium is equal to the theoretical estimate.
Thermal time scale.
Yeah, the thermal time scale.
Yep, cool.
Yeah. So another test we do is to see the code performance. So as I said, we are using the OpenMP parallelization to make the codes to run in parallel. So we would like to test if this parallel scaling is good. And so in figure 6, we have tested that, and mostly it shows some linear scaling performance, and only when the node at each core is too small, the performance to start to decrease. But as a rule of thumb, if like we can just use we can allocate like one node to solve 10,000 nodes, that will be best performance.
Okay, very good. Nice scaling. It's a weak scaling.
Yeah.
Yes. All right. All right. So we've got it verified, it runs efficiently, and now let's do an application.
Yes, so we really want to do is to see how the ice and gas can be supplemented for a membrane common bodies. We would like to make some comparisons with the observation to explain how ice can be preserved in these bodies, and also how their activities can be produced. So in this our first applications, we simulate a spherical body that located at 3 AU.
Okay.
So it's like in the membrane, and to trace the thermal evolutions. And in this figure 7, we plot the evolution from like the beginning of the simulations to almost 200 years later, to show the first column is the temperature, and the second one is the surface ice fraction.
Okay.
And the third one is the gas production rate on the surface. And the final one will be the surface gas number density. So as we showing here, we can see that this body this activity become weaker during the time due to the retreat of the ice front.
Yes. Okay. I follow.
Yes. So
right. Okay.
Then at the end, like 200 years later, the gas ejection rate, the gas production rate will be very low on the body because of the buildup of the dark mantle.
Right. Okay. Very cool. What is the equation of state you use on all this?
The equation of state, I assume is I use the ideal gas law.
Okay. All right. That's good. Just want to check.
Yeah.
Very good.
And so if we go below, and we have in figure 8, this will give more details on how this variable evolved during different time. So we can see it from here is like in the first panel, it shows the evolution of the surface ice fractions at different latitude.
Right.
So in general, the ice in the equator will be like depleted very quickly, just within several days.
Right. Right. You can kind of see this black line here.
Yeah. And for higher latitude, because we are considered near the obliquity here. So for higher latitude, its temperature is lower. So the ice can be preserved in generally much longer. And if the obliquity of this body doesn't change, then we can still to be able to see the ice on its pore in
Right.
like after the like 2.5 billion years.
Yes. Yes. Uh-huh. Uh-huh.
And so, and the rapid consumption of the surface ice is also consistent of the past observation on the comments by the space mission. So in general, there are a very small fraction of surface area are found to have ice.
Okay.
So most of the ice, they are just contained in the subsurface area.
Yes. Okay.
Yes.
Good. Good, good. And then diurnal evolution.
Yes, so in the figure 9, we also show like how the diurnal evolution of the outgassing flags on the bodies. And so, and we can see the at the beginning, these thermal flags is related to the diurnal temperature evolution. And after that, because of the ice is retreating to beneath the surface, and the dust mantle becomes thick. In that case, there is some thermal lake, and we can see that the maximum flux rate will be shifted toward the afternoon side because of the thermal lake.
Yes.
And then eventually it will shift to be less prominent and less dependent on the diurnal evolution for the interior ice sublimation.
Yes, I'm with you. Good.
Yeah.
Makes sense. Makes sense.
Okay. Yeah.
Okay, very good. Interior gas activities.
Yes, so before we are looking at the surface activity, now we are looking more into the interiors activity. So here, yeah, this figure just gives like the ice from profiles at different time step. So as I showed before, like during like 200 years, the gas production rate will be very small, and also the gas number density on the surface is low. That's because at that time the surface ice has been retreated to like around 5 to 10 centimeters beneath the surface.
Okay.
So in that case, a lot of gas, they are consumed when they are float into the towards outward. So most of the ice, they are trapped in the porous region. So they are not actually will emit outward.
Yes. Okay. Yes, that makes sense. Thank you. Okay. Yeah. Interior. And now the activities.
Yes, and in the figure 11, we would like to check the interior gas activities. Indeed. So yeah, and this is also one way to evaluate the abilities of our code, and also to make some comparison with our code with some theoretical understanding. Okay. So and in from previous the thermophysics understanding of the cometary body is like the ice sublimation mainly occurred on the ice in the ice front. So beneath the ice front, the gas density will be equal to the saturation state. So so that's why they beneath that there may not have some ice sublimation, because the surrounding gas has been like in the saturation state. So no more ice can be sublimated and contribute the gas molecular into the surrounding. Cool. So then only at the ice front, the molecular, they can be sublimated and into the region that is empty of ice. So yeah, that's the one of the theoretical understandings. And so in our code, because we solve all the gas and ice and thermal equations, we want to check we can capture that kind of the physics. So in here, and the different color curve is corresponding to the different state at different depths.
Right.
So yeah, and as we can see that when the maybe we can pick the 2 centimeter depth curve, the red curve to see.
Okay.
So yeah, so once the E becomes the front of the when it becomes the ice front, so the ice front is located at 2 centimeters.
Yes.
In below the surface. In that case, we have the ice fraction will be gradually decreased because these ice are sublimated. At the meantime, some of the gas molecular, they can also float inward and to condense on the subsurface. So as we can see in the curve of the depth at center, the orange curve, orange
8.
Yeah, we can see that the ice fraction in that layer actually increased because of the condensation from the upper layer.
Okay.
Yeah.
Cool.
So
Very
cool. So this provide a good validation of the code.
Nice. Very cool.
Yeah, and then another finding we found is when we evaluate the gas production rate, and the gas production rate is almost like, although it's oscillating due to the diurnal evolution, but it's almost constant when the ice front is located in one space region. So like there is, we can see there is a clear jump. That's because the ice front has been retreated to the sub layer. In this case, it will re-establish the equilibrium, and then after that, they will continue this equilibrium to supplement the ice and supplement the gas.
Okay, good. Yes, that makes sense. Good, I'm with you.
Yeah, and another thing we would like to check is that to see if the subsurface, the region that is below the ice front, they can be actually in the saturation state. So here, this figure plot the same thing as before, but now we normalize the gas number density by the saturation.
Okay.
In that case, we can see that when for all the layer that is beneath the ice front, it has a value almost identical to the saturation density.
Okay, which would be 1.
Yes, so which shows that our code can reproduce this physics pretty well.
Nice, very nice. Okay. Very nice. That makes sense. Okay. Figure 12. We got some Newton diffusion coefficients. Ice retreat timescales.
Yeah, another thing we want to examine is the ice retreat timescale. So that's very relevant for the comment about the main-bell comments, because we want to note the lifetime for the ice to contain in their bodies. And then like for the future missions, they can be able to predict what's the depth of the ice on this body.
Right.
And there has been many theoretical and also some numerical study to tackle this issue. And we would like to, sorry, I got a phone call. Yeah.
That's okay, all good. Okay,
let's continue. And so, and this we get use the equations from the Schrödinger and Hensch et al. Of this study to make the comparison.
Okay.
So, and what we deduce is the time scale for the ice retreat is longer than the theoretical result.
Okay.
So for the, and like for example, the equation predict that for the ice retreat time scale for like 8 centimeter will be around 100 and like 13 years. And according to our simulation, it seems to need to take like 200 years more.
Okay.
Yeah. One of the discrepancies will be due to the exist of the gas, the surface gas in our simulation. So since we are solving the surface gas boundary condition using the conservation equation, so we did not assume the pressure on the surface is zero. In that case, there still be some pressure on the surface that can surprise the outgassing.
Yep.
Yeah. And in the theoretical work, they typically assume the pressure is zero. So in that case, so in that case, they can get a faster consumption.
Right. That makes total sense.
Yeah. But in general, though, we have achieved like order of magnitude.
That's pretty impressively large for what it is. Okay.
Yeah, and we can, based on this, we also like to suggest that maybe if for main belt comment, the ice retreat will be also, so it's not very fast. As we can see, to retreat like only 8 centimeters, it will require 200 years.
Okay.
So in that case, the ice can
here we go.
Can survive in some shallower place in such a main belt comment. If they are like their lifetime is like 1 million years, which is equivalent to their collisional lifetime.
Okay. So we'll survive.
Yes.
Cool. Very good.
So that's like provide many hope to find the main belt comment.
Very
to
cool.
find the ice.
Very nice. And the water, and there are, do you want to cover figure 14 at all, or 13, 14?
Yes, so here is to explain like why for the main belt comments, although we call them main belt comments, because we saw the activity is driven by the ice sublimation, but currently is actually no ice or any gas evidence has been detected yet for these bodies. So yeah, we only see there is like repeated and recurrent dust ejections during in like a near perihelion when they are orbit are past the perihelion. So that kind of recurrent activity was more likely linked to the ice sublimation, but there's no evidence for the actually any ice or gas yet. Okay. So in this section, we would like to discuss why that's the issue. So if in the figure 13, we was showing like what's the gas production rate for such a body. So as we can see here, so after like only a few days, because of the rapid consumption of the surface ice, the gas production rate will decrease very fast, and it will decrease below the detection abilities of the current facility. So in that case, even there will be ice, water gas molecular, it will be very hard to detect because the production rate is too low. And also due to the photo dissociation, it will even make this harder to detect.
Go away, right.
Yes.
Okay.
But we also show that in the figure 14, that although the gas production rate is hard to detect, the dust activity can be prolonged. They can be they can still occur in many years. This is because the subsurface gas have a strong enough pressure. They can push the dust on the surface to be ejected.
Yeah.
So in that case, here shows the maximum liftable particle size radius at different time. So in general, we can see that even in 200 years later, there's still some micrometer size or 10 micrometer size particles that can still be ejected from the subsurface, and that could contribute to the observed dust activity for this main-belt body.
Erosion front, yes. Okay, nice.
Yeah, so that's that's our main idea.
Very cool, very nice. And then just to remark, there are 3 very lovely appendices with some verification and validation studies on it. And we do have a shape model, I think that's worth showing on this shape model.
Yeah, in the study, because we want to make some one-to-one comparison with previous study, so we just use a spherical body. But here shows that we can actually model irregular shaped body.
Yay. Okay, very good. Very good. So do check out those appendices, people. And Yoon, I want to thank you so much for walking us through your very lovely PSJ article.
Thank you. Yeah, that's a great pleasure to talk with you.
Thank you. And you mentioned it at a couple of points when we were going through the paper. And so let me push on that a little bit. And where do you think we go with this over the next, let's say 2 to 5 years? Everybody who ever does a software instrument knows that by the time the article is published, the software has already moved on. And so are there new capabilities of the software coming in? Is there additional physics models that can be put in? What's your anticipation for making it open source, etc.? And so just sort of next steps.
Yeah, and I think the current ability of this code will be good enough to model main-belt comments, and we definitely need to further develop this code. So to add like more volatile species that can make it applicable to like general comment in general, to include like CO, CO2, something like that.
Right, more chemistry.
And yeah, more chemistry. And another thing is we also would like to like extend to simulate like the centaurs and maybe KBL. In that case, we also need to consider the phase transition in general. And that's one also we are currently underdeveloped. And the other thing, which is more like more unknown region, is like how to model the erosion of these dust layers that will evolve. Yeah, that will evolve the chemical understanding of this, how the dust particle they can evolve. And yeah. And in that case, we also need to use some other code to first understand this physics, and then we can use that to construct a macroscopic or continuum description of this physics and to implement into the framework of this code. So that's our future goal in the next few years.
Very cool. Well, I really look forward to seeing this software instrument develop, get better, be applied to many different types of comments, and it'll be very exciting.
Yeah, thank you.
All righty. That will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Yeah. Bye. Thank you, everyone.
Thank you.